Hello everybody, so today I will do the system design of WhatsApp deep dives. So I will talk about these two topics, scalability and also one kind of follow-up question, how to support multiple devices for the same user. So yeah, yesterday I did the high-level design, so it looks like this now. And from here, I will think of the scalability. And I will do the quick excuse before this video that I'm so tired today because I worked until 8:30 p.m. today, so bear with me if I'm so slow or I'm so stuck. But that being said, I will start with scalability. So scalability, so I have to support 1 billion daily active users. So I will do the quick math from this. The back of the envelope estimation. So 1 billion daily active users. So I have two concerns here. So one is scalability in terms of the throughput, and the other concern, or I should say other scalability perspective, is the data storage size. So for the throughput, so there are 1 billion daily active users, so definitely I have to think of which one is the most important. So yeah, I think create chat API. Yeah, create chat API is relatively low throughput because, of course, let's compare how often I send a message or versus how often create a new chat room. I can say hundreds of times more frequent for chatting. So I will today focus on this API, real-time messages API. And just be clear, S3 upload media, download media API. This is actually kind of out of concern for us because S3 has these APIs. And that being said, S3 internally does the horizontal scaling, so it does the consistent hashing for the scaling out. So internally this scales infinitely. Even though if we kind of makes a request to specific object very intensively, there should be the kind of rate limit. But in a case, the same image is downloaded by only the users who are in the same chat, probably up to 100. So this is not a big concern. And receive past messages API, yeah. And this is also, not a big concern because this is a bulk, and let's say how often I do make requests as a user. So how many times I open the WhatsApp in a day? Probably once every hour, or maybe twice, 3 times every hour, and keep it open. So this is obviously less frequent messaging. And yeah, about this one, acknowledge messages API. And I just noticed something, so I would like to move this to WebSocket. I don't have to make the independent API for this, so I will do that. Okay, so I will move this acknowledge messages API to here as another command of the WebSocket. Acknowledge message and message ID. Yeah. So that being said, my concern is this API. real-time messaging API. So when I think of this real-time messaging API, as I said quickly before, each server has a kind of mapping from user ID to WebSocket. So now, I will talk about this later, but for now, oh wait a minute, so I will think that each user has one WebSocket, not each chat room. So that being said, our concern is there are so many users who are connected to the WebSocket. And let's say there is one user who sends a message and other users has to subscribe it. So firstly, I will be clear how many users are connected at the same time. So 1 billion daily active user. So let's say, just imagine how many hours my WhatsApp is open. Probably a few hours a day. So let's say there out of 10, 1 billion out of 10 users are connected at the same time. So it should be 100 million connections at the same time. Yeah. So this means that there are 100 million WebSockets here in the server. So obviously this is a big issue because as a rough estimation, each WebSocket is 10 kilobytes. So this means that let's say each server has 250 gigabytes of memory. With this, I can count how many servers I need. So it should be 10 kilobytes. So kilo mega giga, so 10 to the 10 divided by 10 to the 4. So we need 25 million. Yeah, because it's 10 to the 6. So we need 25 million servers. Is this correct? 1 billion daily active users. 100 million connections at a time. So 250 gigabytes and 10 kilobytes. Yeah. Okay. Yeah, so 25 million servers are needed to store the WebSocket for 100 million users. This is kind of huge number. So, but we have to do it, right? Okay, so I stopped the video and quickly checked by myself and noticed that this is number of WebSocket per server. So this means that we need 4 servers needed. So very small number. Okay, so we can even considering the buffer, let's say we need 10 servers. So what happens is that there are 10 servers here for real-time message service. So a user connect to one of these 10 servers with WebSocket, and it is possible that the users who are in the same chat room are not connected to the same server. So let's say user 1 in the chat room is connected to server 1 and user 2 in the chat room is connected to user 2. So in this case, the approach I told before in the previous video doesn't work. So real-time message service doesn't know, because or I should say, the message has to be delivered from user 1 server to user 2 server. So how I can realize is I will use the Redis PubSub. So Redis PubSub is a kind of queue so what happens is the server sends a message, or I should say, okay, so I will talk about Redis PubSub first. So Redis PubSub is like a queue system, queuing. But this is fire and forget type of queue. So in terms of the Kafka, the messages enqueued into Kafka are persisted in the disk. So whatever happens, the message is not lost, and the client, or I should say consumer, can fetch the message later. But for Redis PubSub, this is a push type. So when the message arrives at the Redis PubSub, this pushes the message. This Redis PubSub sends a request to the consumer, like, hey, the message has arrived, this is it. And the thing is, if the consumer is not working at the time, Redis PubSub doesn't retry, so it completely forgets. So that's why it is called fire and publish. And also, the message is not saved in the disk in Redis PubSub. It's only in memory. So, but instead of that, in terms of the durability, Redis PubSub is inferior to Kafka. But Redis PubSub is quite quickly delivers a message because it is in memory. So under the constraints that we need 500 millisecond for the message to be delivered, I use the Redis PubSub. So internal mechanism is, so I create one topic per one chat room. But if I do this, there should be so many topics. Yeah. Let's say each user create, maybe 10 chat rooms. In that case, we have to use 10 billion topics. Yeah, but this is possible. What I have to do is use the Redis cluster for the scalability. So I can think of this queue as completely independent to each other. So I can use Redis cluster to horizontally scale this part. Okay. So now when the user firstly connects to the random server, and then when the server notifies that there is a kind of chat ID, or which means a topic, that server has not subscribed yet, this real-time message service subscribes it, so that the message should be delivered. So in this way, for that user, the message is delivered to that user will be sent to this server. And then, so this is what happens when the user connects to this server with WebSocket. And then when user sends the message, this real-time message service pushes the message to the Redis cluster by specifying the chat ID as a topic. And then this Redis cluster, Redis PubSub publishes the message who are subscribing to the topic, which means that any server which has the connection for the user who is in that chat, and the message is sent to the user. So in this way, the throughput 25 million WebSocket per server is completely handleable, and every time message comes, it just has to publish the message to the Redis PubSub, and the message is routed delivered to other servers. Okay, but of course it is possible that if I store 25 million WebSocket per servers, this server has the kind of CPU intended instead of memory intended. Memory is now fine with 10 servers, but maybe CPU intended, CPU bounded. So in that case, I do the horizontal scaling more. Okay, good. And quickly I return the alternative. The alternative approach is that user should be users in the same chat room are connected to the same physical server by WebSocket. In that way, we don't need Redis PubSub because the the users to whom the message should be sent are in the same server. But this is a kind of annoying problem because the request now becomes a stateless. So when user tries to connect to the server, he has to be actually this doesn't work in our case because, as I said each user per each WebSocket. This means that if two users are in the chat room, they have to be in the same server. So I can kind of say when users are connected through chat, like the graph traversal, they have to be in the same chat. In the server. So one server has to, and I can easily imagine that most of the users are connected to each other by the hops of the chat rooms. So this doesn't work. So yeah, I will use the WebSocket. Redis PubSub here. Okay, so I talked about the scalability of throughput of this real-time message service, but I also think I should quickly mention other part too. So chat service, or I should say API gateway, this is okay because API gateway is internally the cluster of servers. So actually it internally scales out. And for chat service and message service, I can use the horizontal scaling. So because each request are stateless. So servers are scaled out according to the amount of traffic or maybe CPU memory usage. Okay, and for PostgreSQL, as I said, creating the chat doesn't occur so frequently, so I'm almost sure this can handle the write request. But for read request, I can add some read replicas if needed. I don't do this calculation here because I'd like to talk on other things. So yeah, in that way this can be handled. And for DynamoDB, this is about message delivery. So every time a user sends a message, the message record is created. But because, this means that let's say each user sends 10 messages per day. In that case, because 1 billion daily active users, 10 messages per day. One day is 10 to the 5 sec, so it's 10 to the 9, 10 to the 10 divided by, this is 100k requests per sec. So this looks so heavy loaded, but message table has a partition key ID. So internally in DynamoDB, message table is scaled out, or I should say sharded, based on the ID. So I can think of this, that each message ID, each message is stored in a different node according to the consistent hashing. So this doesn't become a problem. And for message delivery, yes, the same, almost the same thing can be said. Even though the number of message delivery records to be created is so many, this is partitioned by user ID. So I can think that in DynamoDB, each server has the message delivery records specific to one user. So obviously this is not so many. This doesn't load the server. And media metadata, yeah, the same thing can be said, because partition key is message ID. Each node in the DynamoDB will not be overloaded. Okay, so now DynamoDB can handle the throughput loaded by this request. So now I've talked about the scalability in terms of the throughput. Okay, so now we'll talk about the scalability in terms of the data size. So now we can see in primary DB, user record, chat record, user chat relation record. So number of user chat relation record is number, wait a minute, no, so chat user. Yeah, so I can say this user chat relation record is the biggest table here, because one user has multiple user chat relation and one chat has multiple user chat relation. So I will calculate only the data size of this table, because others are less than that. So storage. So user chat relation. So 1 billion daily active users, let's say there are 5 billion users in total. Let's say half of them are active daily. Let's say 2B. And let's say each user is belongs to, let's say, 20, maybe 50 chat. So there are 100 billion chat relation records, and let's say each record is 100 byte, because of course we have something like join that or something like that, or maybe he left the chat room. In that case, maybe we need the left add and we have it as the kind of logical derivation. But yeah, so 100 billion times 10 bytes, no, 100 byte is now 100, so this is billion. So 100 times, so this is 1000 kilo, mega, giga, and tera, so 100 terabyte. Let me check. 100 billion times 1 byte is 100 terabyte. Yeah, because million is giga and billion is terabyte. So this is 10 petabyte of data. So this is so big. So what I can do is do the kind of partitioning. To be honest, this is a bit of an annoying problem, because let's say each PostgreSQL has 250 terabytes of storage size disk. We need 40 servers. So I have to do the DB sharding for this, but the problem is if I do the DB sharding, I cannot use the join query. And to be honest, if I do the DB sharding, I would go with the DynamoDB, because if I try to do the DB sharding in PostgreSQL, I have to do the sharding logic in the application code, like the hashing. But of course, I know that there is a kind of infrastructure that I can use multiple PostgreSQL databases as if it is a kind of one single database, or I can use the kind of AWS partner, because partner internally does the sharding, DB sharding, and it works as if it is one database. Yeah. So I would use partner or DynamoDB actually. And in either way, internally, what happens is that it is not possible to do the join in a single database. So what happens is that if I try to do the join query, let's say from user, firstly, all the user IDs, chat IDs, which is associated with that user from UserChatRelation table databases shared it, and then it fetches all the chat IDs from each chatted database. Yeah, so that happens internally. Okay, but yeah, to be honest, I'm surprised that this is too big. But yeah, the basic idea is that okay, just in case, the relation table is 10 petabyte. So chat table is wait a minute. Chat table is, because it totally depends how many. Yeah. So this depends on how many people are in the same chat room. If many people are in the same chat room, the number of chat room is small. But if most of them are one-on-one chat, there are many chat rooms. As that being said, I'm pretty sure most of them are one-on-one chat when I think of the messaging app I'm using. So 1 billion or 2 billion users, and let's assume all of them are one-on-one, and let's say 50 chat rooms, and I can do divided by 2 because 2 people makes 1 chat room, so almost the same, 50 petabyte, no, 5 petabyte. yeah, 5 petabyte of data. So again, I need maybe 80 servers. Wait, 10 petabyte. This is 25. This is 50 servers. For users, we have 2 billion users. And okay. I'm a bit confused. So 100 byte chat room. Petabyte, 25 servers. Yes. Okay. 100 petabyte. Terabyte times 100. Yeah. Okay. So this is 2 billion 50 divided by 200. 5 petabytes. Okay. And user 2 billion users, and each is 100 byte. So this is relatively smaller, but still a lot. So 1 out of 50, so 200 terabyte. So 1 server. I see. Okay, so under this situation, what I can do is kind of using the DynamoDB and create the secondary index. So user can be stored in the thing. Oh yeah. For user, I use the partition key here. It's okay. And for user, okay. So the thing is, I don't use the join query anymore, but the server chat service will make query multiple times to each table. So let's say I'd like to know the chat IDs, chat room IDs who belong to, I mean, that user belongs to. In that case, I get the whole user chat relation records which belong to the user ID, and then from this chat ID, I bulk fetch the chat. So for this access pattern, I can use like this. So user ID is partition key, user chat relationship, user ID is partition key, and chat. Yeah, maybe we can sort this with maybe created at or join that. Yeah, or maybe last message is that. Anyway, for now I will use with chat ID. So in this way, user can know which chat rooms he belongs to. On the other hand, let's say for each chat, I'd like to know who are in that chat room. So for this, I create the secondary index, global secondary index of the DynamoDB. So I create user ID, and here chat ID is the primary key. And user ID is the sort key, or maybe join that is better because I don't know. Yeah, sorting logic is something based on the product decision, so I just put it sort key as user ID. But with this global secondary index, if user would like to know who are in the same chat room, firstly it fetches the chat record. User chat relation global secondary index, because chat ID is the partition key, Then for those user IDs, chat service makes the second request to get all the user data in a bulk and returns it to the user. And now frontend can render all the users in the same chat room. I mean, in that chat room. I think this is a kind of approach in which I don't have to do the sharding by myself. Okay, so now we talk about the messages size. So for message metadata, I will omit the discussion on this because obviously comparing the message with media metadata and messages without media, Rudder is much more. So I will talk about message and message delivery. So, but to be honest, this is partitioned by user ID here and message ID. So in terms of the storage, it doesn't become the problem because, as I said, DynamoDB partitions the data according to the partition key. But I will just quickly calculate how big it is. So there are 1 billion data active users. Let's say 10 messages are sent per user, and let's assume one message is 100 bytes. So with this 1 billion, well, as I said, 1 billion corresponds to 1 terabyte, and 10 and 100, so this is 1 petabyte. This is so huge, but as I said, this is, stored in DynamoDB and partitioned by message ID. Okay. And message delivery, so this is 1 billion daily active user, and let's say there are on average 1 user, or maybe 2 or 3, or let's say 3 message delivery records to be created on average. Then there are 10 messages per day, so this is 3 petabyte. But again, this is partitioned by user ID, so it's totally fine. Okay, good. So the thing is, I use the DynamoDB and partition key by DynamoDB. That helps a lot. Okay, so now I will talk about the next topic: how to support multiple devices for the same user. So this is actually so easy. So here I create device table. So device belongs to the user ID, and should say user ID device registered at, or maybe logging in at, blah blah blah. So, and the thing is, here for message delivery, this is created per device ID, because the message has to be sent to all the devices of the user. Okay. And something I have to mention is, as I said before, so this real-time message service creates the message metadata and message delivery at the same time in the same transaction. So, and in DynamoDB, there is a kind of upper limit on the number of records which are updated in the same transaction atomically. I think it was 100 or something. So the thing is, if the user registers so many devices, let's say one user has 10 devices and there are 100 users in the same chat room, it becomes 100 times 10 is 1000, which is more than 100. So this is a problem. So probably what I would do is set the upper limit of the devices which can be registered per user, like 2 or maybe 3. Then I also set the upper limit of the number of users in the same in the same chat room, like 30. So in that way we can do 3 times 30 is 90, which is less than 100. So probably I will do it until there is a specific demand for the so big rooms. Okay. But to be honest, now I'm thinking that upper limit 30 is quite low, because one class, let's say university class, has 50 or 60 users, students. Okay, so this is a kind of interesting discussion, I think. So I will quickly talk about this. So how can I handle more than 100 transactions at the same time? So the problem here is I try to create the same record, multiple message delivery in the one transaction. So instead of that, I will kind of introduce Kafka for that, or I should say, no, from message I will create from this DynamoDB. I use a CDC. So in case of DynamoDB, the kind of CDC is called DynamoDB stream. In my understand, if my memory is correct. So from Dynamo stream, I create this message delivery code. So I will kind of register AWS Lambda as a trigger. So and when the message created, Dynamo stream triggers the AWS Lambda and the message delivery is created. Of course, this Dynamo AWS Lambda references devices, we go here and create message delivery. But there is one problem here. So if I do this when the user sends the message acknowledge to the real-time message service, it is possible that this message delivery has not been created yet. So my idea here is I will create another queue. So I will call it acknowledge queue. And this real-time service pushes the acknowledge record. And the good thing is this acknowledge queue worker can update the message delivery record with acknowledge, the acknowledge attribute of the message delivery record. So this worker fetches acknowledge record and update acknowledged at timestamp. So in this way, I can kind of specify like maybe 10 or 20 seconds of the delay for this acknowledge worker to process a new message. So in that way, I can almost make sure that I can make it almost certain that message delivery record is already created. Or if there is some problem in DynamoDB stream and message delivery is not created yet, still acknowledge worker can retry to fetch from acknowledge queue and update it acknowledge at later. Okay, so today I talked about the scalability and also how to support multiple devices for the same user. And also in the end, I could kind of remove the limitations that up to 100 transaction can be made, has to be made, which means number of average devices in the chat user times number of upper limit in the user has to be less than 99. Now we don't have to, we are not limited to that constraint. Okay, that being said, I finished my today's call system design practice. Thank you so much. Bye bye.